Alright, let's get started. Not a whole lot in the way of major announcements because obviously we just started. First homework's going to come out on Friday. You'll kind of get a feel for what's going to be on that homework after today's lecture. Today I would say is the day where things start finally getting real. So what I mean by that is you all are probably I hope you're well familiar, given who you had for structural analysis. I would hope so. That's a jerk. So you all are probably well familiar, I would hope so, with a problem like this. So it's like 1.2 kips per foot, and I'm just making this up. There's nothing magic about this. Let's say 24 feet. Now, if I gave you that problem, hopefully by now you could perform all of the necessary analysis. So determine the reactions, draw a shear diagram, draw a moment diagram. I mean, I get it might have been a while, at the very least, for those of you that had me last semester for this, it's been since, the fall semester. And if you had me last year, even further, or it might even be longer than that. But with enough time and review, you could do this, right? Okay, but one of the things that we never really answered in structural analysis was, where the heck does this come from? In other words, here we are in the Weisberg Applied Engineering Complex at Marshall University. How do I turn this into that, right? And we need to be able to do that because this is something that we can analyze. I can determine shears, I can determine moments, deflections, and once I understand that stuff, I can then determine, well, how deep does this beam need to be in order to safely resist those shears and moments? How much rebar do I need to put in this beam so that it's safe? How deep does it need to be so that it doesn't deflect so much? That is design in a nutshell. But none of that makes or has any value if we can't turn this into this, right? So that's what we're going to do today. We're going to start to dive into that process, how we take a real-life structure and turn it into a model that we can then analyze. And then we'll spend the rest of the semester talking about designs. Like I said, it starts getting real today. So I think you all will have a lot of fun with this. Now, where this starts is with the determination of something called tributary area, and I'll explain that here in a sec. I just want to give a real super quick recap of what we talked about last time. So last time we talked about design philosophy. How do we go about designing something? What's our process? We mentioned the idea of a factor of safety. The idea is that we could compute a strength, but then adjust it by some number, some magic number, that would account for uncertainties and things like that. The problem with that is that there's all sorts of uncertainties associated with the loads, associated with the resistances, and so we use a little bit more of a refined approach where ultimately what our goal is we determine the uncertainties associated with the resistance and the loads, and then we adjust the loads accordingly and adjust the resistances accordingly so that we manage the probability of failure. In other words, there's no structure that's perfectly safe, but what we can do is design a system or component such that we manage that probability of failure and keep that probability of failure low and uniform. And that's something that we can guarantee. And so the philosophy that we use, LRFD, sometimes it's called ultimate strength design, that philosophy maintains or helps to ensure not a perfectly safe structure, but a structure with structures, I should say not a structure, but structures with low and uniform probabilities of failure. And that's the idea. So what we would do is we would adjust the resistances by these resistance factors. These are lowercase phi values, and we'll discuss those later. Then we adjust our loads with various load factors as well. And all of those values are these quote-unquote magic numbers that adjust these loads and resistances such that we get uniform levels of safety. So we're gonna don't worry if the Greek and all the weird equations was a lot. Don't worry, we'll digest that. I mean that's something we'll be exploring throughout the semester, so it's not something I expect you to understand on day one. What I want to do today is I want to talk about the loads, and I want to talk about the system itself. In other words, how do we take a system like a building or even something like a bridge, any structural system, and take that and turn it into this, something that we can analyze and something that we can assess. And in order to do that, one of the first fundamental concepts that you need to understand is what's called tributary area. So Tributary area is the means by which we basically turn a structure into this. Now, what we're all revolving around is the discussion of loads. We talked about loads a little bit last time, the different types of loads that structures are subjected to. We typically in structural engineering are dealing with 5 load events. The dead load, the self-weight of the structure. We're dealing with the live load, or the load related to the structure's occupancy, what the structure is being used for. And then we have a series of environmental loads. And the big 3 that we're usually worried about are wind effects, snow effects, and the effects due to earthquakes or seismicity. And in order to assess the effects of those loads on a structure, that's where the tributary area comes into play. So I've been talking about tributary area for the past couple minutes. What is tributary area? Well, in a nutshell, the tributary area is the means by which we define how much a given element of a structure is responsible for. In other words, if I'm talking about, let's say, a floor beam, okay, so I've got a big Weisberg Applied Engineering complex, and there's oodles and oodles of floor beams above our heads that's supporting the weight of the floor above us, right? So there's all sorts of floor beams up here supporting the weight of the second story. The tributary area of, let's say there's a beam right here, okay? So the tributary area of this beam is how much floor area of the floor that this beam is responsible for. Once you understand that, you can begin the first step of turning that floor beam into a model that we can analyze. And so typically when we look at floor beams and we look at tributary area, it's best defined as the area that's bounded halfway to the next adjacent element. And so the way that I tend to draw that out is, okay, so let's say we've got a floor system, and you're going to have to bear with me on my 3-dimensional artwork here. Hold on. There we go. Okay. So let's say I have a floor system, and we're talking about reinforced concrete here. So let's say I've got, this is a floor beam, this is a floor beam, this is a floor beam, and I'm just going to draw 3 of them. But this could go on forever. It really doesn't matter. And let's draw this in 3 dimensions. So it sort of goes like that, goes like that, goes like that, like that. So that's my floor system. Does that make sense? Does that kind of come across? Okay. And so let's say that I'm looking at this floor beam. Okay, so I'm looking at this one. What I propose is that the tributary area for this floor beam is the area bounded by the region that's halfway over to the next adjacent beam on either side. So in other words, this beam is responsible for all of the floor, that's all of this floor up until this point, because from here, this beam takes over. So on this side, it's all of this floor up until here, and then past that, this beam takes over. So if I wanted to maybe draw that in or shade it, I would say that that is the tributary area, because that line right there is halfway over to the next beam, next adjacent beam, and the one on the left is halfway over. So this is sort of the halfway point between this beam and this beam. This one is halfway between here and here. And so all of this floor area is what that beam is responsible for. Does that make sense? Is everybody okay with that? And so that's for beams, okay? Let's say we were talking about columns, okay? So if we're talking about columns, okay, so imagine that I'm in sort of a helicopter looking down on a building. The columns would look like just a big grid, like a big, maybe like rectangular grid of columns, right? So this is me in the helicopter looking down. Does that make sense? Okay. And so these little squares sticking up, those are the columns sticking up out of the ground, right? And so what I would do is I would pick any one of these columns, let's say this one right here. And I would say it's responsible for all of the area halfway over to the next one, or halfway over to the next one, or halfway over here. So its tributary area might be, I don't know, something like this. And that's the tributary area for that column. Does that make sense? If I was talking about, let's say, a corner column, its tributary area would be that, just halfway over to the next column. If the center column, it's going to have the biggest. So if you're looking at gravity loads, the columns in buildings that have the heaviest load typically are the center columns. Whereas if we're talking about the edge columns or the corner columns, if we're talking about the floor load, they see the smallest amount of the floor load. Does that make sense? Everybody okay with this? Okay, all right. So the idea is if I've got a given generic floor plan, so this is sort of what I drew on the previous slide, and I'm going to throw some terminology at it so that you're aware. So here's the floor plan. So this is me in the helicopter looking down, right? So we're looking in plan view. Here, these squares are the columns, okay? Now, I'll go ahead and tell you that I'm probably going to use the term beam and the term girder a little bit interchangeably, but typically what I'm trying to do is a little bit of a hip bone connected to the leg bone type of thing. The idea is that the beams frame into the girders, and the girders frame into the columns. Columns go down to the ground. That makes sense? So if we're looking at a floor system like this, let's take a look at these elements. I would propose that the beam is going to be responsible for the smallest amount of floor area. So if I'm talking about this beam that the arrow is pointing to, it's going to be responsible for all of this. All the floor area that's halfway over to the next adjacent beam, and then the next adjacent beam takes over, and so on and so forth. Whereas if I'm talking about the girders are going to be responsible for for everything that's halfway to the next adjacent girder. So the way the girders are oriented, they're going to be responsible for much more floor area. Does that make sense? So like if I'm looking at this A2, B2 girder, it's going to be responsible for all of that. Does that make sense? So let me ask you this. If I was looking at a building, what do you think is typically going to be a bigger element, the beams or the girders? The girders, because the girders are responsible for more floor system. The idea is that the beams frame into the girders frame into the columns go down to the ground. And then again, the columns, they're just going to be responsible for that square grid area halfway over to the next adjacent element. Everybody okay with me on that? Okay. So, and ultimately what we'll be able to do is turn that into this. And I'll show you how we'll do that with an example here in a second. And if what I'm saying, I guess if it's still a little hard to perceive, if you can't quite see it, here's a real example. So this is a picture that I took in the parking garage on 3rd Avenue, right down here. You can see the basketball court or basketball arena right across the street. And so this is a perfect example of beams framing into girders framing into columns, so on and so forth. So these are the floor beams that are supporting the weight of the parked cars on the story above, right? Okay, and so look what's happening. Those floor beams are framing into this girder. The girder is then framing into this column, and the column is ultimately transmitting that load down to the ground. And you can see, it's a little difficult to see, but you can kind of see how if you look at the size of that girder versus the size of these floor beams, it's much wider and much deeper because it's subjected to much more floor load. Make sense? And then if you're looking at each one of these individual floor beams, like if I'm looking at, I don't know, that one right there, then this one is going to be responsible for all of that floor, and then maybe like all of that floor right there. That's what it's responsible for. Does that make sense? So what we're going to be doing here in a second is what's called a load takedown. And what a load takedown basically means is I have a structure, I have a framing system, I've got some load applied to it, and the idea is, okay, let's take this load, let's take this framing system, and let's start asking for each one of these elements, what do I need to design this element for? What do I need to design the beam for, the girder for, the column for, so on and so forth, and then I can begin my, my structural design. Make sense? Okay. So, here's what we're going to do. We're going to start off by doing a floor takedown of a very, very basic framing system under a very basic loading condition. Okay, now right off the bat, I want to illustrate to you a lot of how we specify structural loads for systems. And a lot of times what we're doing is we're specifying these loads in terms of pounds per square foot. And we'll take that and turn it into this. Okay? And so what we've got here is we have a system that's subjected to 20 pounds per square foot. Now, I want to be honest, 20 pounds per square foot is not a lot. Okay? It's really not that much load. 20 pounds per square foot is like the minimum specified snow load on structure. So it's really not a lot of load. But you're going to see here in a second how 20 pounds per square foot can turn into 120 kips on a column very easily. Okay? This stuff, it's crazy how just a small little bit of load can turn into something serious. Okay? And what we're going to be doing is with this distributed load, we're going to be looking at some various elements in the system, and then we're going to take this and determine, okay, what would be the distributed load on a typical interior beam? What would be the concentrated loads on a typical girder? What would be the axial loads on a column, and so on and so forth? So there's going to be some connections to CE312 here in a second. Now here's the floor system. Okay, so I want to make sure that everybody's clear on this. So we have a structure that has 4 columns along one direction, 4 columns along another. Typically, when you look at floor plans for building systems, your columns will be denoted usually by letters on one direction and numbers on another, sort of like an Excel spreadsheet, so that if you're discussing a column with another person, you could say, I'm having trouble with that B6 column design or whatnot, so that everybody's speaking the same language. I have a system here that's very, very basic. It's very grid-like, very rectangular, but you can have some really funky floor layouts. I mean, typically a structural engineering project is not going to be this pretty. I mean, they're going to be laid out in various configurations, because a rectangular building is kind of boring. It's just a box. Engineers love it, architects and the public hate them. So you've got to have something a little more interesting. Now, a couple other engineering terms to throw at you. I would refer to this building as being 3 bays wide and 3 bays long. The bays being sort of these regions, these rectangular regions between columns. So this would be a bay. So there's 1, 2, 3 bays, and 1, 2, 3 bays. So that's what we're talking about. Now, let me also be clear. There are some instances where this design is very, very practical or very, very expected. One place where you can see this type of design all the time is a Walmart. You've been inside a Walmart and actually looked at the structure. It's just it's a grid of columns. That's all it is. It's actually a pretty easy design once you have your loading figured out. With the building is 150 foot wide, we'll say east to west, if up is north. So east to west, and then the north to south dimensions 90 foot long, and the bays are 30 feet by 50 feet. And as for the interior floor beams, they're spaced at 10 foot on center. Everybody okay with this? Okay. Now, one of the things about a building like this is that if you look at all of the typical interior floor beams, like let's just pick one. Let's just pick that right there. Would you agree that the tributary area for this floor beam would look something about like that? Would you agree with that? So that's the tributary area. I would argue that every one of these interior beams are all going to have the same tributary area. I would also argue they're all the same length. They're subjected to the same interior floor load of 20 pounds per square foot. In other words, from a designer's perspective, once I've designed this beam, I've designed all of them, except for a few. There's a couple beams I haven't designed, And there's these ones over here on the edge. Why are these ones on the edge different than the ones inside? Only half the tributary area, so only half the load. So these ones on the edge could theoretically be a little bit smaller than the ones in the middle. Make sense? Now, this, let me be clear, this is only if all we were talking about is gravity load. If we were talking about lateral load, you know, wind and seismic, then maybe we would need to include some bracing systems inside the structure. And if that's the case, maybe a couple of those exterior elements might be a little bit beefier. But under gravity load, the edge beams are going to be a little bit smaller than the interior beams. Make sense? Okay, so let's draw some of this out. Now, we have girder C2, D2. So that's this girder right here. Again, halfway up, halfway up. So we're talking about maybe this. And then the next one is column B2. B2 is an interior column. So that's this one right here. So again, halfway to this one, halfway to this one, halfway to this one, halfway to that one. So the tributary area for that might look something, I don't know, about like that. So, and notice how technically it should hug that tributary, that green one I drew over there. And so that would be your tributary area for that column. I know I sort of just did that for you, but does that make sense?
Why is it that large? I'm confused.
Because since we're talking about columns, this column is responsible for halfway over to this one. Which would be right here. This column responsible for halfway over to this one. This column halfway over to this one, and so on and so forth.
Okay, thank you.
No problem. No problem. That's what we're here for. Any other questions? It's good stuff. Okay. Now, that's great. What do I do with this? Okay, what do I do with this? Let's take a look at what we can do with it. So let's look at example 1. Everybody read that? Okay, so let's look at a floor beam. Okay. Now, I'm going to copy this picture. Come on. Okay, never mind. We'll just sort of put this over here. All right, let's take a look at this. Okay, so we're looking at one of the floor beams. Somebody help me out. How long are the floor beams, the interior floor beams inside the building?
30 feet.
They're 30 foot long. Okay, so we got a 30 foot long beam. Okay. Now help me out with this. That, what we're going to call here, the length is this. How wide is that? What would the dimension be? What is this width, total width? 10 feet, right? Because 5 feet on one end, 5 feet on the other, right? And so what I'm going to do is I'm going to call that the tributary width. We'll call it W sub T. We're going to say that's 10 feet. So therefore, the tributary area in this case would be 300 square feet. Okay with that? Okay. We're not directly going to use the AT value right now, but we will here in a second, or we'll at least reference it, and you'll see why. Okay. All right. Now, let's test my 3D art skills again. So we've got floor system, and these are reinforced concrete elements. So we got this, got this, got this. And that's enough. Okay. All right. And so the floor system goes like that. Like that. Okay. Now, if I remember correctly, this dimension from our floor system is going to be 10 feet, right? Because that's how far the floor beams are spaced out, right? And what you told me was the tributary width of this system was just that, it was 10 feet. But remember, this floor system is subjected to an applied load. So what I did to this floor system is I said, I'm going to place a pressure load on this system that's 20 pounds per square foot. So I imagine I've got a 20 pounds per square foot pressure load applied over the entire system. So every square foot of the building, I got 20 pounds. Right? So this is 20 pounds per square foot. Now, if I'm looking at this particular floor beam, this one right here, that floor beam is only responsible for halfway over, halfway over. So this shaded load right here, that's what that beam is responsible for. And help me out again. Give me one second. Help me out. What was this width again? 10 feet. So here's what we're going to do. What I want to do is I want to take this three-dimensional floor system, and I want to see if I could take that beam over here and isolate it. I just want to look at the beam. I don't want to look at the floor system, just the beam. And I want to see if I can turn that pressure load into a distributed load on that beam, much like this. Because that's starting to turn this into a system that I can analyze. Okay? And the math is really, really simple. Okay? Let's just keep this basic. What is the floor load on the system again? Somebody tell me. How much load am I putting on the system?
20 pounds.
20 pounds per square foot. Now, how much width? What's the width of the floor that one beam is responsible for? 10 feet. So I have 20 pounds per square foot applied over a width of 10 feet. So 20 pounds per square foot for a distance of 10 feet is how many pounds per foot? 200 pounds per foot. It's that simple, right? So I propose that this 20 pounds per square foot pressure load can be collected onto a single beam, and that single beam sees 200 pounds per foot. In other words, if you want the equation, the distributed load on a beam is the pressure load times the tributary width. So 20 pounds per square foot times 10 feet, 200 pounds per foot. Sound good? So therefore, now remind me, how long was this beam again?
30 feet.
30 feet. So what you're telling me is I have a beam that's 30 foot long that's being subjected to a 200 pound per foot distributed load. Right? I'm going to take my time on that because I want to make sure that makes sense. So that's taking a floor system, turning that into this, into something that we can all analyze, right? And from this, we should be able to determine everything that we need in order to be able to design this, right? Yes.
How do you know the reactions at both ends? How did you choose those, or are those just kind of arbitrary for now?
You're talking about the fact that it's simply supported?
Yes.
Oh, that's a great question, and let me say this. I'll give you a short answer now, but by the end of the semester, you'll have a very clear understanding of why that is.
Okay.
But the short answer that I'll give you is this, and I'm going to go back to actually my physical example of 3rd Avenue. So here's my 3rd Avenue parking garage, and so my 3rd Avenue parking garage, what I'm looking at in this example is something like this, okay? Now, if you recall from structural analysis, we had really 3 types of support conditions that we considered. We had the roller, which just had a reaction this way. We had a hinge, which had reactions this way and this way. And then we had a fixed support. Okay? Make sense? Now, let me ask you a question. Would this problem, so let's take this problem. You all can draw the shear diagram and the moment diagram for this, right? Y'all remember this, right? The shear diagram, what do? Go up, and then linear, right? And then we have the moment diagram, a lot to a little, little to a lot. Make sense? Okay. Let me ask you a question. Would this at all change if I turn that into the roller and that into the simple support? Would it really be any different? No, right? This has the same moment diagram as the previous problem. Same shear diagram, same deflection, same everything. So much so that these and these in a whole bunch of structural engineering scenarios are sort of treated the same. And we sort of call them simple supports. Okay? Whereas this one, that's a lot different. And the reason it's a lot different is because as soon as I fix that in, remember if we had a beam that looked like this and it had a fixed support like that, this support behaves a lot differently because not only does it have a reaction that goes like that, but it also has a moment reaction, right? So that does change what the moment diagram looks like. So these conditions we call fixed supports. So it really doesn't matter whether or not we're dealing with this or this because they sort of behave the same way. It's really whether or not we deal with a simple support or a fixed support. Now we're in reinforced concrete design. So what would be a real world example of a simple support versus a pin support? Here's a real world example. I'll erase this. Simple supports would be something like this. Here's a column. We have this little part that sticks out. We call that a corbel. And the beam sits on it. That's a simple support. Whereas a fixed support, the column and the beam are cast together. Right? Okay, that's a fixed support. So the question really isn't whether or not we're dealing with this, it's whether or not we're dealing with simple supports or fixed supports. So it's actually a really great question that you ought to ask is, am I using the right one? Now I'm asking you, if we were dealing with a building like this, and I was looking at the floor beams, would you say simple supports or would you say fixed supports? I'm asking you. I would say they're simple because those floor beams aren't cast integrally with the girders like that. They're just sat in. There might be some epoxy grouting or something like that, but they're not monolithically cast like this. That's not to say we don't do that, but just not for typical interior floor segments. It's a great question. Does that answer? Everybody else good with that? This is good stuff. And this, if you ever see these little concrete nubs sticking out, the support beams, we call those corbels. Terminology and random factoids. Sound good? Any questions? All right. Now, watch this. let's take this system, this floor beam, and let's analyze it a little bit, okay? I want somebody to tell me what the reactions are. 3,000 what?
Pounds.
Pounds, exactly right. And I'll go ahead and tell you. Let me ask you, do you think this math is pretty simple? Math in this course is actually it's not that bad. It's a lot of, there's some formulas that are a little long, but it's a lot of add, subtract, multiply, and divide. But what's going to get you are the units in this course, just going to tell you. So make sure that you're cognizant of that, because it's really easy to throw a kip where a pound should be, and it's really easy to throw a foot where an inch should be. So I'm just throwing that out there. So yeah, so exactly right. The reactions are going to be 200 pounds per foot times 30 foot divided by 2, and so that's 6,000 over 2, 3,000 pounds. Sometimes structural engineers just draw it. I know y'all probably think that's a hashtag, but they used to be called pounds too. So. Hashtag reinforced concrete. All right. Okay, so just shorthand in case you see that on some counts. Sound good? Okay. So from here, I could draw the shear diagram. I could say, okay, here's the shear diagram. I'm going to go up 3,000. I'm going to go, so it's a linear, or it's a constant load, so a constant slope on the shear diagram, go down to negative 3,000, and then go back up, right? And then from there, I could draw the moment diagram, so on and so forth. I'm not going to do that here. I'm just illustrating that you could do that. Is that okay? Okay. Now, there's a point I want to make about this, but before I do, does anybody have any questions about what we've done here? Okay. So on this problem, I want to assess not just the floor beams, but I want to assess the girders and I want to assess the columns. Okay? So I want to look at the girders, but before I look at the girders, I want to point something out. Does everybody have all of this? Okay, so let's look at the girders. Now I want to actually see if this image will copy. There we go. All right, let's look at the girders. In this case, we're looking at girder, I think it was B2, B3, is that it?
C2, D2.
C2, D2. Let me ask you a question. That floor beam we just did, what were the reactions again? 3,000 pounds? Okay, so you're telling me I have a floor beam in the building and the ends are seeing 3,000 pounds. Where does that 3,000 pounds go?
Columns.
Columns, that's one place it goes. Where's another place it goes?
Connecting girder.
Connecting girders, right? Look at this image, right? I have a floor beam that goes from here over to the next adjacent girder, right? The ends of those girders, let's say they're seeing what, 3,000 pounds? So if I was looking at, let's say, that girder, I propose that I've got a girder that looks like this, but everywhere that I have a floor beam, like right here, I'm going to have a point load. Right here, a point load. Right here, a point load. Right here, a point load. What are those point loads? The reactions from the floor beams. Make sense? See what I mean? Those reactions don't just magically go, they go to the girders. See, let's look at the floor system. Let's go back to the image of what the floor system looks like. See, here's the system that we're looking at, and we're looking at this girder, right? What is this girder seeing? Well, we've got this, and they're framing into the girders, right? So the floor beams connect to the girders. Girders frame to the columns. Columns go down to the ground. Make sense? So here's what I propose. Now, how many frame in here? Here's the girder. How long is the girder? 50 feet. And so I've got framing in at every, 10 feet? So I've got a girder that's 50 foot long, and I'm going to have a point load every 10 feet. And those point loads are going to be from the beams. So I want to ask you, so far, based on what we've said, would you agree that the model for this girder is going to look like this? Got a girder, this dimension, 50 foot long, and every 10 feet, I'm going to have a point load. That'd be a fair statement? Now, $64,000 question, how much is each one of those point loads?
Aren't they the 3,000?
Is it 3,000?
6,000.
Why are you saying 6,000?
Both sides.
There you go. If I'm looking at C2D2, here's my floor system, here's C2D2, look, there's a beam here that contributes 3,000, but there's a beam here that contributes 3,000. What do you think? Not too bad, right? So each one of these, now let me be clear. Somebody point out a girder where it would be 3,000. On the outer edge, so maybe like an A1B1 or a B4C4. One of those, it would be 3,000. But the ones on the inside, it's going to be 6,000 because there's one on each end. Make sense? So I would propose that the analytical model for the girders, this is going to be 2R. 2R. Or, R equals 3,000. 2R is 6,000. Now, I tell you what, if you want to make sure that your notation is, correct, maybe call these RBs. RBs. So that way it's beam reaction. I wasn't, super precise with my notation. We'll just say RB for beam reaction.
-1.
What?
That's -1.
Now, it's 7 mistakes per semester, but -1 for that is a bit extreme, considering that I'm the one that keeps score, so we're going to go with -0.04. We would have gone with 0.08, but you had to bring it up, so. Okay. All right. Now, help me out. Each one of these are 6,000 pounds. So let's just do a real quick structural analysis. Somebody tell me, what are the girder reactions going to be? So, what are RG? What's that going to be? You're saying 12,000, right? Because I've got, 1, 2, 3, 4, so I've got 8 beam reactions, so 4 on either side, right? Everything's symmetric. So you're telling me that the girder reaction is 1/2 of 8 RB so 12,000 pounds. Everybody okay with that? Bless you. So far so good? Here's where things get really neat. You're going to like this. The columns, there's 2 ways to do it. We'll show you the columns real quick. Somebody help me out. What is the tributary area of this column? How wide is this? What's the width this way?
50.
50. What's the width this way?
30.
30, right? Okay. So, watch this. So, I'm going to say column method 1 column method 2. So method 1, the tributary area you're saying is 50 foot wide, 30 foot tall. What's 50 times 30?
1,500.
1,500. So what was the pressure load on the floor system? 20 pounds per square foot. So 20 pounds per square foot over an area of 1,500 square foot is what? What is that? $20 times 1,500 is what, 30,000? So 30,000 pounds or what? 30 kips? That's one way of determining the load on a column. Here's the other way. Remind me, what was the beam reaction and what was the girder reaction? What was the beam reaction? 3,000. We'll say 3 kips. And this one was what, 12 kips? Look at this. Here's my floor system. If I look at the interior column, how many girders are framing into that column? 2. How many beams are framing into that column? See, there was a reason when we were looking at this girder, we didn't look at these beams, because we figured, oh, they'll just go right to the column. So you're telling me 2 girders, 2 beams frame into this column. So maybe one way of determining the load on this column is to say that the load on that column is 2 beam reactions plus 2 girder reactions. So 2 times 3 kips plus 2 times 12 kips. And what is that?
30 kips.
30 kips. I mean, it's like day 2, and I've already got room to do a marker drop. I mean,
That's an eraser.
you're right, it is a race. My coffee hasn't kicked in. We're going to go, okay, you get your .04 mistake back. Okay, so we're at .08 already on day 2. Does that make sense? Now, here's one thing, though, to keep in mind. Okay, so what I'm saying is that's 30 kips on that column, but that is only from one story. Okay, so imagine, let's be clear, imagine that, and I'm just going to put this over here off to the side. Imagine that here's the ground, right? So here's the ground, and here's my building. And I'm looking at it off to the side. I'm messing this up. I was doing good on the 3D stuff, and then I've got this. That's good enough. So that's from actually, I might have one. Okay, so let's say I have a building and it's got 4 different stories, like 4 different floor systems. So if I'm looking at like this column segment right here, it's going to be seeing 30 kips of compressive force, right? But what about this column? What, that story, how much force is in the column on that story?
That plus the weight of the previous.
Exactly, so this one's going to be seeing 60 kips. What about this one? 90 kips. So, just from this really, really light load, you could easily get 120 kips of load on the ground. See what I mean? Really easy for that to happen. Really easy. Okay? Does that make sense? So I just wanted you to sort of see how we can take a floor loading and break it down into, items that make sense. So if I'm in column design, design that column to withstand 120 kips. If I'm in beam design that beam to be a 30-foot long beam to withstand whatever 200 pounds per foot, right? Make sense? That's sort of where we're starting with this. So on Friday, you're going to get a homework assignment that's about like taking floor systems and doing this, okay? I'm going to go ahead and end it here, but I do want to mention one thing. What we're going to talk about next time is where we get the 20 pounds per square foot. Like, where did that number come from? Because the other stuff comes like from the architect and from your individual project. But we're going to talk next time about the loads themselves. We'll talk, for instance, about like live loads. Like, what does 50 pounds per square foot look like? What does 100 or 150 pounds per square foot look like? Where do you get snow loads and things of that nature? So that's what we're going to talk about next time, is where those loads actually come from. And then you'll have a homework assignment sort of collating all that. And then we'll actually start getting into some concrete. All right, that's all I got.